Assalamualaikum warahmatullahi wabarakatuh. We are from Group 5. The topic for our project is using eigenvalues and eigenvectors to find stability and solve ODEs. These are our team members: Nur Anisa Najwa binti Zamri, Nur Umaira Akalili Kasim, Siti Zara Safa binti Sani, Nurul Adriana Natasha binti Jamaluddin. These are the contents for this topic. First, introduction. Second, methodology. Third, results and discussion. Fourth, conclusion. Introduction. Eigenvalues play a critical role in the modeling and the control of chemical processes. These controls are controlled by differential equations and system steadiness that might be stable and damped, undamped, or unstable and fluctuating with increasing amplitude. Stability is studied using differential equations obtained from the signals developed by sensors or by real data. Such equations depict as to how the system will operate under these conditions. This section also elucidates how to solve linear ODEs using eigenvalues as well as determining system stability.
We begin by representing the chemical process as a set of ordinary differential equation orders. This equation describes the dynamic of the system over time. To make the system easy to analyze, we express it in a metric form as dx over dt equal to ax, where a is the coefficient metric and x represents the state vector. To analyze the stability, we calculate the eigenvalue of the coefficient metric by solving the characteristic equation determinant A minus lambda I equal to 0, which means finding the determinant of the metric A minus lambda times the identity matrix. Here, lambda represents the eigenvalue. Once we found the eigenvalue, we determine the eigenvector by solving equation A minus lambda I equal multiply V equal to 0, where V is the eigenvector corresponding to each eigenvalue. This eigenvector indicates the direction of growth or decay in the system. This step was carried out using both manual calculation and computational tools like Mathematica to ensure accuracy and efficiency. Finally, we analyze the eigenvector to determine the system stability. If any eigenvalue has a positive real part, the system is unstable, as this indicates exponential growth in certain state. If all eigenvalues have negative real parts, the system is stable, as it will return to equilibrium after disturbance. Complex eigenvalue with real parts can be oscillatory behavior, which can be damped or undamped depending on the sign of real part. To verify our finding, we apply the root stability test. The test uses the characteristic polynomial to quickly determine the number of roots with positive or zero real part, providing a secondary check for the stability classification. By combining eigenvalue analysis with the root stability test, we ensure a thorough understanding of the system stability and behavior.
Once we understand the methodology, we can implement it right away. So as we can see here, there are two differential equations, which is dx over dt equals to 4x plus 8y, and the second one is dy over dt equals to 10x plus 2y. And then once we were given this type of equations, we need to change it into matrix form. As we can see here, I already write it as A equal to 4, 8, 10, and 2 in matrix form. Next, we need to find the eigenvalue. So in order to find the eigenvalues, we need to use the formula, which is determinant A minus with lambda I which is the identity matrix, equals to 0. So from the matrix A that we got before, we need to substitute into the formula and solve it until we get the eigenvalue. So the eigenvalue for this question, the first one is 12 and the second one is negative 6. So once we get the eigenvalue, we can determine whether the system is stabilized or not. So from our first eigenvalue, which is 12, it shows that the real part is positive. But our second eigenvalue is negative 6. That means the real part is negative. So if we were to compare these two eigenvalues, since it has a positive real part, so the system is automatically is unstable.
Verification for both lambda. So for the first lambda, which is equal to 12, we need to multiply the matrix A with vector 1, 1. We get the vector value by substitute the value of matrix A and lambda into the formula A minus lambda IV equal to 0. And then we will get 12, 12 as the result, which is equivalent to 12 multiplied with 1, 1. To verify the next lambda, which is equal to negative 6, we need to do the same thing as the slide before, and then we will get negative 24, 30 as the result, which is equivalent to negative 6 multiplied with 4, negative 5. Next, I will explain the importance of eigenvalues and eigenvectors in understanding system behavior, especially in the context of ordinary differential equations or ODEs. Eigenvalues indicate a system stability. If the real parts of all eigenvalues are negative, the system is stable. Positive real parts means instability, where deviations grow, and zero real part indicate marginal stability. Eigenvectors, on the other hand, show how the system changes in specific directions. They describe the independent components of the system evaluation, providing insight into how a system behaves in each of these directions. Together, eigenvalues and eigenvectors simplify solving ODEs by breaking the system into simpler parts. They help us understand the behavior of each part independently and predict the overall system evaluation. This process is important in fields like engineering and science, where stability and directional responses are critical for analysis. In summary, eigenvalues and eigenvectors are like a roadmap for understanding and predicting how systems evolve. They help us analyze stability, respond to different starting points, and are essential tools in many disciplines.
Conclusion: in analyzing and governing such chemical processes, eigenvalues are of great importance. They offer information about the stability of system by solving linear ODE and classify the stability into damped, undamped, and unstable condition. With these mathematical tools, engineers can guarantee steady process operation and avoid typical risks that may lead to the loss of life and assets or efficiency of production processes in the chemical industry. That's all from us. Thank you.